So I was given a task to talk about databases today, advanced databases, and which is a bit difficult in the sense that, what should I talk about? What does advanced mean? What does data management mean? Well, data management is something that's very well defined, but what does advanced mean? That's a bit tricky. So what I decided to do is we're going to have 2 hours. In the first hour, I want to talk about a bit. I'm assuming you all have a background in let's see. In the first hour, I want to talk a bit about recent trends in data management. I'm going to assume you all have a bit of knowledge about databases, relational databases. You don't think?
I don't think so. I think there's a number of life science people around.
Yeah.
We perhaps have used them, but relatively little knowledge of the internals. I don't know. Ask.
It's absolutely fine. I'm going to stay very much on a high level, and I want to talk about I'm just going to give a bit of historic background about relational databases, what they've been optimized for. Then I want to move to NoSQL databases, the recent trends we all heard about, these MapReduce systems. We'll talk a little bit about that, give a high-level overview of that, and then still move to connected to the Human Brain Project and to scientific data management, and talk about why these new systems, even though they are new and they respond to new trends in data management, why they're still not sufficient or why they still don't cover everything. And then in the second hour, I want to talk about what we have done in connection with the Human Brain Project, or initially with the Blue Brain Project, the database algorithms that we have developed, or the indexing methods that we have developed. And I think also there, a bit of background in databases will help you definitely, but I don't think it's strictly necessary. Okay, I have a lot of stuff packed. I'm going to see how far we get. I think I can take shortcuts whatever we do. Okay, so some data management history. It generally basically all started with banks, right? Initially, banks kept all their files on paper, which was, of course, technology at the time. But the issue was that once customers became more mobile, once there were more branches, once ATMs became prevalent, you needed some sort of central repository to keep your data at. You have your account, you want to have whatever branch you want you want to make sure that your account balance is being kept track of. So at some point in the 60s and 70s, computers were starting to be used for banking applications. And the question was, what about, can we do about reliability, about security, consistency, response time, as well as scalability, right? Today's scalability for banks may not be the biggest issue right now. These days, I think they just struggle to survive, but still, response time, consistency, reliability are very important properties of any type of banking applications. If you go to a bank, you want to be able to deposit money, or most more importantly, probably, you want to be able to withdraw money. So, what the database community has developed is basically a very simple system. A database, one place, a structure where you can deposit or store your data structure that you can access remotely, that has some concurrency guarantees, that has some security guarantees, and it also has a certain decent response time. So that was basically really, banking was really the driving application for database management in the past. And what was developed over years, over decades of research, and also over decades of engineering in companies like IBM and Oracle, is the relational database. It's very simple. I'm not sure how familiar you are with relational databases, but the principle is very simple. It's a very structured schema-based organization of data, and you put all your data in tables. As many tables as you need, and you store tables have all columns where you store different types of information, and you have rows where you store different tuples of information. And you store like this. This one here, this example here shows a very simple example of customer data. You store everything. You basically take the information you want to store, you map it on these tables, and then you split these tables so that you arrive at multiple tables, but such that whenever you have an update, you only need to touch one table. And to then retrieve that information, you have to spread it out over several tables, basically join these tables together and retrieve the information. And for joining this, or for retrieving information, also for input, for putting in information into the tables, we have this sort of SQL, this general purpose query language with which we can formulate queries on the database, on the tables, to retrieve that information. And a very simple example for these two tables is you basically say, I would like to select everything from the tables here, customer city, where the city.city, this column here is equals to the city.city column there. To join these two tables together such that you get all your customers in all the languages. Now, one really important aspect of relational databases in the past has been transactions, or strong consistency, and the ACID properties. How many of you have heard of the ACID properties? Well, that's still a good amount of people. So basically, ACID properties means that when you operate on a database, when you make insertions, but most importantly insertions or updates, there are certain guarantees that the database will make. The A in ACID stands for atomicity, which means that every operation is going to be either executed as a whole or not at all. C is for consistency, which means once you execute an operation on the database, it's going to be again in a consistent state. I means isolation. That is, every operation, even though you may execute several operations at the same time, the isolation means that each operation will be executed as if it was alone, And then finally, durability, which means if your database system crashes, you want to have a log record of everything that has been, all the updates that have been applied. And these are really important properties for banking applications, right? Crash, the durability of the database crashes, you really want to keep track of your latest update to your balance, particularly if it went up. And these strong consistency properties have been driving the development of databases in the last couple of decades. Now I want to highlight two particular aspects of the relational databases that are really crucial for banking applications and that are very much very deep inside the database design today. One is transactions. I've loosely defined it before as operations, right? The transaction is basically something, a series of operations you want to execute as a goal. Let's make an example here. So the question is, why do we need to manage concurrent access to the database? So the example here is we have John and Jane who both want to withdraw $50 and $100 from a common account. And we do this both in this sequence of operations. Both get the balance, both check what the balance is, they update the balance, or they basically deduct $50 and $100, and then finally they update the balance, they write it back to the database result. So the initial balance is $300. Now, the question is, what is the final balance? If both these series of operations are executed at the same time. Does anybody know what it is? Final balance is?
I'll give you the best.
Sorry. It's kind of a trick question, right? It really depends on the order of execution of these two series of operations, because if both start at the same time, they're more or less sequenced at this point here, they'll have different values for balance, and it really then depends who gets to write to the database first. So there's a sort of a race conditions and a condition we cannot really predict the outcome. So what the idea really is now in the database system is that you wrap this in sort of a transaction, which is what I referred to before as atomicity. You wrap this in transaction, and then you say, hey, this transaction is going to be executed full, or it's not going to be executed at all. And then also the I property of ACID, which is isolation. If you execute these two as transactions, each of them should be executed, the result should be as if they were executed alone. So it doesn't really matter in what order the operation they are executed materially. And of course this limits your throughput, right? That limits your scalability, because if you do it naively, you just say, well, this is a transaction, just going to execute John first, and then I'm going to execute chain, or the other way around. So, you know, some parts of the system, of your database system, may be underused, underutilized. And so the question is, how can this be optimized? And there's a lot of research went into how can we scale transactions, how can we speed them up, particularly if you have two transactions. Here, in this case here, they both touch this balance, right? But what if they touch different pieces of data, then you can just execute them? Oh, it doesn't matter. It doesn't matter at all. It only matters if they access the same piece of information, particularly if you want to write the same piece of information. So a lot of research went into optimizing transaction execution, and that has had a tremendous impact on the design of database systems, as I said in recent years. And what the point I'm going to make later on is that while transactions are really important for banking applications, there's now a whole array of applications like scientific data management and web application where transactions are not needed anymore, or at least not that much. Now another aspect that was important, or still is, for banking applications is indexing. It's also important for other applications, but the way it's been done for banking applications is very, very simple, very, very straightforward. For example, you have a whole database, one big table with all the customers, with all the accounts. Each of them has a balance, and you're going to find exactly the accounts where the balance is 900. So what can you do? You could technically really just scan out the whole table, but that's going to be costly. You have to read the entire table from the disk and then scan over it. So what has been done is to develop acceleration structures or auxiliary structures, like, for example, the B tree. Right? B tree, what you can do, the way this optimizes this problem, is by sorting the whole table on disk. It sorts it according to balance, and then puts on top this sort of structure here, this tree structure, and it's really just a B tree that you can use to then locate the accounts with balances 900. So we start at the root, then we scroll through. If it's bigger than 800, you go to 900. If it's bigger than 900, you go to 900. This node here, and they define on this the exact value, the exact account, and have a balance of 900. That's an efficient optimization. And it works well for one-dimensional data. The point I want to make later on is that it's really just efficient for one-dimensional applications. It's really, I don't want to say it's just efficient for banking applications, I'm sure there's other applications as well, but data has become a bit more complex, particularly in scientific application. So, database systems today are optimized for online transactions, for banking applications, and they're also optimized for business intelligence, which is essentially, like for example, the indexing example I made before, where you want to retrieve how many customers do we have that have more than balance and bigger than 920, how many customers do we have that bought Coke with chips and all these kinds of things together. So that's business intelligence, and that's what database systems have been optimized for. But there's new applications now. There's more requirements. There's web applications, which don't care as much about transactions anymore. You know, for example, your news feed on Facebook. I mean, it doesn't really matter. You're not going to be really upset if the order of items isn't correct or if there's one cat picture missing. But you're going to be really upset if your balance in the bank is wrong. So there's different requirements there. And then also scientific applications that I'm going to talk about most in the second hour, which also have different applications, where the queries have changed, but also the data has changed, and that requires updates to those algorithms, data management algorithms. And then what has also changed is hardware. So there's, in the olden days, or not that long ago, we basically assumed the processor, memory, and the disk. That's the system that database runs on. Now we have new hardware. We have non-volatile memory, we have SSD, we have multi-cores, which make it with many levels of processors, which make it very interesting and challenging to execute transactions. So the hardware has also changed. So I kind of already alluded to the conclusion that relational databases, as great as they are, were as they are, one size does not fit all. Not all applications are really well served by relational databases. There are new applications and they have new requirements, right? I mentioned already, strong consistency asset is not required for web applications. It's typically also not required for scientific applications, particularly in the simulation sciences where you basically write all the data once. You may manually fit and write some aggregates and so on. There's not going to be, or there's rarely going to be any update. And even if there are, you're in control of the application. If there's any concurrency issues, you can resolve them yourself much easier. And the problem is that ASIC limits scalability, and that's a big issue for web applications. Right? Particularly small startups these days want to make sure that in the off chance that they're actually going to be very successful, they can scale easily to large numbers of customers. Then another issue is schema evolution is challenging with relational databases, right? I made this little example with two tables, one about customers, one about the city. And in SQL, if your data layout changes, if your requirement changes, it's very challenging to update the schema. You have to go and change tables, you have to add tables, and so on. That's also an issue for web applications that are typically a bit faster. Then there's little optimization for local hardware. Although that's coming, a lot of research is being done for SSD type of memory and also for multi-cores to execute transactions. Also, SQL is a bit of a cumbersome language. It really depends on what your requirements are, but queries can become very complicated, very convoluted, and for many applications, you just need much simpler API. And then finally, we have very limited data types in relational databases in SQL. We have reals, we have floats, we have strings, boolean, date, and any combination thereof. But that's pretty much it, at least what is defined. Most database vendors give you additional data types, but then queries become unportable and so on. So the data types are really limited, and that has been an issue for a lot of applications. For example, if you have XML, if your data is XML, with a relational database, what you typically have to do is you have to shred it, you have to get all the content out of the XML, you have to map it up to a schema, and then when you need to get it back, you need to again transform it into XML, and the question really is, why not just store it as XML? Right. So that's why over the last couple of years this NoSQL movement started, and when it says NoSQL, I mean that's more of a marketing term these days. It's kind of like not only SQL. I think it's a better definition of not just relation. The main objective of this movement is, and several databases or database system classes of NoSQL systems came out of it. The main objective is really to scale substantially better, to do away with a lot of these optimizations of transactions like language that we have in relational database systems, to do away with them and to make sure that we can scale substantially better. And it's done quite simply. We give up a lot of the consistency guarantees. We give up ASIC to improve performance essentially. And also, the interface is in contrast with SQL. It's much simpler for some of these systems. You just have a put operation, write operation, and a read operation, and that's about it. But that's what a lot of applications need. And then finally, we typically also have a flexible scale. Now, I mentioned already, we have several different classes of these NoSQL systems. We have key value stores, I'm going to talk about each one in a bit more detail. We have key value stores, where we simply store a key and value pair, or multiple thereof. We have document stores, which kind of go to this idea that I mentioned before. If all your data is in XML or in JSON, why bother transforming it into a relational schema and getting it back again? Why not just store it as it is and retrieve it as it is so you can use it in your application? Then there's also a class of system called Scalable SQL systems. That kind of goes called NoSQL, which is the idea there is to make existing SQL systems, relational databases scale much better by giving up some of the ACID properties of all of them, and also to use local hardware. And then finally we have large-scale data processing systems. I'm sure you have heard of MapReduce Hadoo, Spark, maybe and others as well, where you just use commodity cluster to do your data processing on, and also to some degree query processing. So let me start by talking about key value stores. Key value stores are very simple. You store a pair of keys and values, really. That's all there is. And so when I write there, create file system or database, it really is, you kind of your key in this sense, if you want to use this comparison, your key is the file system path, the file path, right? And the value is the file. So it's really, it's very much like a file system. It's just four objects associated with one key. And you only have one primary index, and you look up by key. Right? Just give it the key, looks up, gives you back the result, the value, the object. There's no secondary indexes, and there are no transactions, or there's only single multi-update transactions. So basically, every operation is in itself a transaction and is guaranteed to have ACID properties, but you cannot have transactions with several different key value pairs at the same time. And this scales really well. If you have a key value store with a lot of content, with a lot of data, and a lot of clients that are accessing this key value store, you can simply scale it out, right? You can simply say, parts of my keys or parts of my key value pairs, 1 to keys 1 to 10 are going to be stored in one machine, the next one, 11 to 50, are going to be stored in another different machine, and finally the rest, 51 to 55, is going to be stored on the third machine. And you basically need just a directory. The client is going to say, I want to retrieve the value of this key. You're going to go to directory, it's going to be told where this key is being stored, the value of this key is being stored, and then sends it on to one of these machines, one for the sites on. So basically, it's really very scalable if you have a reasonably well distributed access pattern that requests different keys reasonably distributed. Then you can use this idea to just scale out without any issues. Of course, you have to think about how you would distribute the keys. Really depends on what you're looking for. If you have certain keys that are hit a lot, retrieved a lot, then you want to spread them out over different machines or several machines. And the API for key value stores is very, very simple. As I said already, it's a key with the keys and values and key and value pairs. You can actually think of it as in relational terms, as a table which has two columns, one with key and one with value, and that's what it's going to be stored in. And so the API, yes, you have insert, key and value, you have lookup with the key, you have get next, and also delete. That's all there is. Now, there are, as I said, there's a very limited form of transactions here, and very importantly, there's not very many as such, it's just this API you have at your disposal. And of course, that was the initial idea of key value stores. People have already started to develop more complex languages on top of key value stores, on top of this API. But in itself, the idea really is that key value stores don't have any query language. Okay. So the next type of NoSQL system are document stores. I said it before, the idea really is if you did this on an XML or a JSON in some funny format, you don't want to insert or you don't want to shred it and insert it in the relational database. You just want to insert this snippet in the database and get it out again. Now, what is a JSON snippet or what is an XML piece of XML? I think most of you are familiar with XML. You see this basically semi-structured description of data, and JSON is quite simply a complex version of XML. So an example is given here. This is an object or a JSON snippet and where we have an ID of 1, a name with green door and price of 12.50 and certain tags. Right. So it's basically a bunch of key value pairs in a snippet. There are different implementations of them. Some of you may be familiar with SimpleDB, CouchDB, one for MongoDB, which are very, really famous implementation of document stores, and they enable scalability very well in the sense that SimpleDB and CouchDB, for example, they replicate. That means they replicate your entire database. So if you have a lot of requests, a lot of queries on the database, you can simply put it on different machines and then redirect queries as to balance the load. And then, for example, MongoDB is using sharding. That means that certain snippets of documents are going to be on one machine, others are going to be on another machine. Also, there the idea is to balance the load. If you have multiple requests, if you have one snippet, if there's a few snippets that are going to be requested a lot, you just divide them and move it to two machines. Yes.
What happens if you've replicated it and somebody deletes an item? Is that sort of covered in this simple scheme?
Yes, absolutely. So it's going to be deleted on all machines where it is. Yes. So the operations are very, very simple. You basically insert information into it. It's just the user. You insert a little snippet, right? With this, with these three attributes. If you want to retrieve it, you also send in a small JSON snippet where you say first the attribute or the key first should be John, and then you get back the snippet here. If you want to update, you retrieve the object in whatever way you want. You can go by down here or by username or by the first name, and then you can set certain properties. You set age to 40 and salary to 7,000. That's one of the interesting aspects of document source here is really that you can also add attributes on the go. So that counts for the flexible schema. You can just change your schema as you wish. For example, the example here is that salary is being added. We didn't have this initial, which is added as a key and a value. So you can really change the schema on the go. And finally, the last basic operation is to remove data snippets, which is basically deleting depending on what you specify. So the operation here as well is very simple. There are very few operations, no complex language, and I mean that's really one of the interesting aspects. We already have this with key value stores, a flexible schema, because you just add key values as you wish. But here we have a bit more structure, and we have the ability to add or change the schema in a bit more structured way. But this schema change, as much as the advocates of MongoDB praise it, it also has its challenges. Right? I'm going to make an example here. In this example, or these two examples, we insert two different objects, two different snippets in the database. One is a vacuum cleaner into the inventory database. Right, and we say the model is 14Q3, manufacturer is X17, and we insert this information stock, these quantities 25 and so on. So basic information about it. Then we insert another vacuum cleaner, model 14Q2. For this, we insert an attribute color. And we can do this as a flexible schema, but the problem is, what is it that we're going to get back when we actually try to get all the vacuum cleaners? One object is going to have, one snippet is going to have a stock attribute The other is going to have a color attribute. I mean, it's great, it's a flexible schema, but we have to take care of that in the code that then actually deals with the snippet. And that's very, very hard. I mean, no, it's very hard. I mean, it's certainly doable, but it's a challenge in itself. I don't want to come across as an advocate for relational database systems, but it's just one has to be careful when dealing with these aspects, because with a relational database system, you have a clear contact with the database. You know exactly what your schema is. So the code that inserts data to the database has to conform to that, as does the code that reads it out. So with that, I can kind of verify that I'm not getting total garbage out of the database. But here, what I have to do, I actually need to figure out, to verify that the system is going to work properly. So I have to go and get the code that inserts the data, and I have to compare with the code that retrieves the data. It's really, I mean, you get benefits, and if flexible schema is really something that's important for application, by all means, do something like this. But there's also, I mean, it's not going to come for free. You will have to account for the flexible schema in your code, in the code that deals with the results, the query results. So, with that, I want to move on to kind of new SQL systems, scalable relation systems that basically try to address, again, some of the shortcomings of NoSQL. Because NoSQL does not offer any type of large-scale transactions, as by and large doesn't allow for any transactions. And so what new SQL systems try to do is add in transaction. So we basically in relational database systems throughout all the transactional properties, right, to NoSQL systems, and now we're adding them back in again in new SQL systems. But so what new SQL systems try to do is really get back some of the functionality that we lost back into it again and make sure that it's still efficient. The way this is done is, for example, MongoDB, which is a main memory database, is, I mean, what they said is, look, I mean, main memory is getting bigger. Why don't we just run the entire database in main memory? It makes it much simpler. It makes transactions much more efficient. You don't have to go to this anymore. And so MongoDB is actually a transactional SQL system that is still is efficient. So basically, with new SQL, what the database community is trying to do is get back in some of the properties we lost, but in a scalable way. Yes?
In case of these in-memory databases, is there a big chunk of database stored in memory, or is all of it stored in the memory? So for example, if I have a 1 terabyte database, can I still run it on a system with 500 gigabytes of RAM?
So, I mean, the idea really is, for example, MongoDB is that everything is in main memory. And if the database is too big, we just spread it out over several machines, because it's in main memory transactions and that touch several different machines are still going to be reasonably efficient. So main memory machines are really about keeping all the data in main memory. Whereas, I mean, it's a bit, you're making a very good point in the sense that also traditional relational systems, they keep a large chunk of the data in main memory, of course, for caching purposes. But main memory databases keep everything in memory. Okay, with that, I'd like to move on to scalable data processing. Scalable data processing, or MapReduce Hadoo and others, has basically come about because amounts of data have been growing very fast. And we need scalable ways of analyzing this data, of querying this data. And it's nothing fundamentally new. If you parallelize things, typically they get faster. But parallelization is hard, right? First, you need to have a problem that is parallelizable. And you need to be able to see it as such and to actually parallelize it. It's not straightforward. Then you need fault tolerance, because if you scale out commodity machines or even a supercomputing system, you need to deal with big failures of machines. So you need some sort of fault tolerance, and that's difficult to program or to implement yourself. Then you need mechanisms to distribute the data. It's a lot of data, several machines will take care of it, several machines will analyze it, so we need to distribute data. Then you need to load balance. Some of these machines may get a lot of work, others may not get a lot of work, so you need to balance a bit what they need to do. And then you need to set up all the infrastructure that does this, right? The fault tolerant state distribution. It's not a trivial task to do this. Right? And so what MapReduce, the guys at Google proposed MapReduce initially, what they proposed is to a new programming model that comes along with an implementation for a library. Programming model, the idea is essentially that you think about your problem in two phases, and I'm going to talk about that in the next slide. That makes it very easy to parallelize this computation, and then also they propose to have a library that does all the really difficult stuff like parallelization, fault state distribution. Right. And so the programming model is quite simple. You have, again, pairs of key values, right? And at the beginning of the application is the input data, which is transformed into key value pairs, and now comes again key value pairs in the end. And we're using for MapReduce, it's nothing fundamentally new, but we're trying to use two abstractions. One is map and the other is reduce. Map task will take in key value pairs that will produce intermediate key value pairs, and the reduce task will then take these intermediate key value pairs and produce the output key value pairs. That's really all there is to it. So you need to think of your problem as a map, as in two phases, in the map phase and the reduce phase. And then the library that comes with it is basically, it aggregates all the intermediate values associated with the same intermediate key, and then passes this on to the next phase, which will the reduce phase, which will then compute the result. I think it's best to make an example here. It's a very simple example, standard example from MapReduce, which is about counting words in the document. It's not the most interesting application, but it's at least one that can be parallelized very easily. So we have an input file with two lines, one with apple, orange, mango, and one with mango, grapes, and plums. We're going to go in three phases. One is the map phase, right, the first phase. Then the shuffle phase to redistribute data, and then finally the reduce phase that will compute the final result. So what we do initially is we split the input file into two lines and distribute them, send them to two machines, which we'll call the mappers, right? They will take in these lines and will produce key value pairs, which is what they're supposed to do, right? So out of each word, they're going to make a key value pair. The key is the word, the value is how often this has occurred. Right? We have mango 1, grapes 1, plum 1 for the first, for the top mapper data. So that's the map phase. You just produce this sort of intermediary key value pairs. Then in the shuffle phase, what we do is we redistribute the data. We send this to the reducers, and we also here use two reducers, two separate machines for the other reducers. And the idea here is that we send all the key value pairs with the same key to the same reducer. So quite simply, for example, we send mango and plum to the top reducer and grapes to the bottom reducer. And then, because we do have mango here on the bottom mapper, we send this also to the other reducers, taking on the other mango and the other two tuples to the bottom reducer. Right? So what we then have is we have all the key value pairs, all the intermediate key value pairs with the same key at the same reducer, and the reducer then has to count top them up, right? Mango we saw twice, basically reduce the key value pairs, and then finally we report the entire result, which is not that exciting in the sense that only mango actually appeared twice, but that's the final result, right? That's how this works. Now, of course, this is a very simple example of counting words. In reality, when you set up any sort of MapReduce task, what you need to do is you need to implement the map phase and the reduce phase. And this can be something way more complicated, of course, than counting words. And
do you have to set up the shuffle phase as well, or is that taken care of by the...
That's taken care of. That's taken care of. But that's one of the, in my opinion, bigger issues, because as soon as your problem gets interesting, you have tons of data, and shifting this data around is really, really costly. What's more is that, what I haven't mentioned is that at the bottom of this you have the HDFS, which is trying to account for failures. So what's actually happening is that all the tuples by default and in default setup will be replicated 3 times at different reducers. So that in case one of them fails, it's available someplace else. That just means more traffic. Now, in this example, I just shown this with 2 MapReduce reducers. You can of course scale this out massively. And you can also use the same machine as a map and reduce, it doesn't matter so much. System will then, if the map is busy, it won't use it as a reducer and so on. It will balance the load. So this, in essence, scales very, very well if you have a problem that is parallelizing. There's a lot of, I think there's a bit of misconception about MapReduce is that it gives you something for free. Or well, it does give you something for free, but it's not a parallelization. It is really, you yourself have to think about how do I map this to MapReduce or to the map phase and reduce phase. And if you have a problem with a lot of data, with a lot of common state, it's going to be very, very difficult to make it scale. So there's no free parallelization here, you have to do it yourself. It's just that the abstraction of MapReduce helps you think about how to parallelize it easily. And so yeah, and really the shuffle phase is you're going to exchange a lot of data during the shuffle phase. So that is really a challenge to still keep this system scalable. Okay, so just to So just to get back to the different systems or different classes of the NoSQL systems, key value stores. There are several of those. I'm just going to mention Cassandra, an Apache project that is kind of the reference implementation today. Document stores, I mentioned already, you have CouchDB and MongoDB, which are used broadly. Scalable SQL systems, I just want to mention MongoDB there, and then finally database, data processing systems. There we have Hadoo, and for example Spark, which is analytics on top of Hadoo. Just maybe as just a clear maybe confusion, MapReduce is the Google project which has never been released publicly, and Hadoo is basically the Java implementation of MapReduce done by the Apache Foundation. Now, there's a lot of people who say, who will make you believe that, you know, all these new systems are replacing relational databases. I think I have a bit of slightly different view on it, in the sense that these systems are all kind of new points in the design space. It really depends on what your problem is, what do you want to use. And I've seen really. I sometimes try to work with startups once in a while, and I've seen really terrible things, in the sense that there was I think it's an electioneering company that do statistics to help candidates to plan their election campaigns. And somebody there told me they had this Oracle system relational database, and it was too complicated, it was getting too slow for them, and so they replaced it with MongoDB. And I was talking to them, and it made absolutely no sense to replace it with MongoDB. They had absolutely no requirements that would hint at anything that MongoDB could do. Nothing like their data was really very well structured. It was a clear schema. There were no changes. You don't need a flexible schema. So it doesn't make much sense to go to MongoDB. But still, they claimed they were at least a couple of X faster than on the relational databases. And my suspicion simply was that this was more down to bad design on bad implementation or lack of optimization of the relation system. But it really depends on what your problem is. And so I try to kind of show the data management landscape. You can do this in arbitrary ways. I use the x-axis, the query analysis and frequency, and on the y-axis what I call the structureness, how structured your data is. And the way I would look at this is, if you have very, very few queries, if you have very, very few analyses that you want to run, and you have just arbitrary files, no structure at all, you may want to use Hadoo instead. That makes sense because you implement the MapReduce case yourself. That will read the files in which the data is stored. You easily do that, right? Then, if you have a bit more, a bit higher frequency of analysis and you have a bit more structure, you may want to use MongoDB CouchDB as document source. Really also there depends on whether or not you have what your data is natively in. If it's already in XML, fairly structured, then this might be a good idea. Or you may also want to use Cassandra as a key value store. If you have a high analysis query frequency and you have solid structure, then you should probably go for traditional relational databases like Oracle, MySQL, or also Postgres. And then finally, if you have very, very high analysis frequency, I think one really reasonable thing to do is use something like MongoDB to really give you the response time that you want. So, I mean, this is, as I've written already, this is the data management landscape. According to me, it really depends on what your requirements are. And you could really, you can easily replace all of these on both axes with other aspects that are important for your particular problem. But my most important question now is, what about scientific data? Because that's what I do, that's the research I do. How well is it supported by current relational database systems and the NoSQL systems that I've just mentioned? And scientific data is different from banking applications. It is, I already mentioned it. You don't have any update, or you have any updates. You have rarely have updates. It's mostly read-only data, or write once, read several times. And the data in the scientific application is typically also not very well, cannot be mapped easily on tables. It's not dimensional data, it's very unstructured data sometimes, and it's really ugly data to deal with. And then lastly, it's also massive in size, and that means indexing is considered overhead, like you see the B-tree index. That can be quite an overhead if you have to do this for gigabytes and terabytes of data. And so many of the database optimizations are irrelevant. And that kind of motivates, obviously, of course, also my research. Now, I'm kind of running out of time, so what I would like to do is I'm just going to jump ahead and connect to the Human Brain Project, or the Blue Brain Project, with which I have been working now for quite a while. I just want to make two examples about where we see data in the Human Brain Project. I'm going to talk about brain simulation as well as medical informatics. These are the two sub-projects for HPC. There's two sub-projects that I'm involved in the Human Brain Project. So the brain simulation, and I apologize here for everybody who knows something about brain simulation. I'm kind of doubling down quite a bit. But what is happening for simulating brain is before building a model is, or what goes into building a brain model, at least in the Blue Brain Project, is there's a lot of literature going into it. So you need to know certain parameters of certain cells are coming from literature, so the literature needs to be analyzed. There is a lot of neuroscience data that's already, like atlases, that's already structured data. And then finally there's lab data, some of it actually produced by the Blue Brain Project, the scientists there in Lausanne. They do produce some of this data themselves. All these three modalities go into a model that is then simulated on a supercomputer, and what comes out is essentially time series of activity voltage over time. Right? very simple, and if to make this a bit more fancy, you can also visualize this. Right. So we have, and what goes in is really literature search, right? Research there, the neuroscience data, so our databases already provide to a large group of INCF, and the final app data. And what comes out is a massive simulation result. These are really just time series that need to be analyzed. They call up recorder voltage in each of the compartments of the model simulated over time, and the size of it, of this simulation result, depends on the size of the model. Right? The bigger the model, the more typically the bigger the result will be, because you just record the voltage of every compartment, every part of the neuron, and then also of course the result set size depends on the length of the simulation, both of which, size of model and length of simulation, typically are constrained by the simulation infrastructure. And what basically is coming out is well, this terabytes of data, time series that need to be. So that's the simulation. This is the data involved in the simulation aspect of the project. Then another sub-project is medical informatics. There, what we're trying to do is integrate federated clinical information from different hospitals while preserving data privacy. So what we want to do is we want to integrate data from these hospitals in order to define disease signatures. Exactly. We want to find objective definition of disease, because diagnosing, particularly brain disease, is difficult, because oftentimes it depends on information given by the patient, who in itself is already impaired and cannot give you very, very detailed information. So what we want to try to find is an objective definition of disease. And the way we want to do this is by integrating this hospital information, and that's based on patient record, patient history, which is really, by the way, it's really unstructured data, because it deals with mostly notes written by doctors, which is a pain in the neck to do anything useful with.
Reading them would be a trouble to start with, isn't it?
Sorry?
Reading a doctor's handwriting is the first problem, isn't it?
Yeah, absolutely. And you know, I mean, I've been in charge of doing the anonymization on the patient records, and it's a nightmare, because we have some structured information, we have phone numbers, right? We have email addresses, we have addresses, we have everything. We can remove that. If it's structured, it's easy. But then you read through the free text, and there's phone numbers of relatives. It's a nightmare. Anyway, so we can still get information out of it, right? We can get important information on age, like first visit, like some sort of when the MRIs were made, and so on. So we still get some information out of it, though most of the doctors' house you can just forget about it. Very difficult to make good use of. So then we have also MRIs, from which we extract features like sizes of certain brain regions. Then we have information like protein markers, and then finally genetic information, SNPs. And what we try to do is basically a clustering on this information. We try to find what distinguishes healthy patients from unhealthy patients, in order to find the disease. And this information is going to be used for diagnosis, to improve diagnosis. But then also in the context of the Human Brain Project, we want to model the sick or the healthy brain using the healthy brain, but also the sick brain, and that information is going to go back into this. So the data management and the HPP, I just want to briefly show where I see the basic areas where data management, data analysis, data processing is needed. First, the literature analysis, and that's going to go into the simulation, into building models for simulation. There, I think Martin Telfon is already using Hadoo to process this information. This is quite challenging, but I mean, it's tons of data, so much literature that we can only do this with Hadoo. Then the neuroscience data collection, they're already stored. These are already stored in relational databases, because this is very, very well structured information. There's nothing funny about this, so MySQL, basically relational databases can be used for it. The same goes for lab data. This is not a lot of data. This is all hand. Basically, what I mean by lab data is really patch count data and microscope data. This is all very small data, small amounts of data, very well curated, and this can also be stored in relational database if it has to be stored in relational database or in the database. It's really not that much information. Then we have streaming time series and analytics. These are two different things. Streaming data time series, we've been contemplating about analyzing the simulation results once they stream out of the supercomputer directly with something like Storm or Spark, right? And so I'm not sure if it's going to be done, but some system like this, like one of these two, would be adequate for such a task. Analytics, as we do them in the medical informatics sub-project, their Spark would be would be adequate, and we're probably going to use it to some degree. The problem there is that we cannot move most of the patient data, and Spark, which is essentially data analysis of Hadoo, Spark assumes everything to be centralized. So we're trying to figure out what we can do there. And there's a lot of research. We're not just dealing with patient data stored at hospitals, we're also dealing with research data coming from pharmaceutical companies, and this is data, still a lot, that we need to use as well. Then, yes, so for the last 3 points, static time series data, static time series analysis, there we really lack something really efficient, something good to use. Also for spatial data, and there's not much available for spatial data, and yet this is one of in building the models for the Blue Brain project in the past has been really a bottleneck, and that's what I'm going to talk about in a second down there. But more needs to be done. And then finally, the distributed data integrations as well. What I mean by that is really the patient data at the hospitals. They're not all NoSQL systems, systems, or in relational database system is going to help us much. There, what we're doing right now is developing our own solution in order to make sure that the data stays at the hospitals, but yet still within query and get reasonable results. So with that, I would like to conclude here. Just to summarize, the data management has undergone tremendous changes. Some of you, I'm sure, have had databases 101, maybe undergrads, right? You dealt with SQL, you dealt with normalization, probably relational algebra, and all these kind of boring things. And the good news is, well, the bad news is it's not entirely irrelevant now. There's new systems, more interesting systems, in my opinion, driven by new requirements and new use cases, web applications where you need to be able to scale out, and also what's more interesting to me is scientific applications. I simply don't need to, I also need to scale, I simply don't need any support for transactions at all. Still, the current needs of scientific applications are not served well, in my opinion. Better job would be done there, and that's what drives my research. And particularly, like I said before, spatial data, large-scale analysis, and also the integrated of data to preserve privacy. These are all aspects that are currently not well addressed by today's systems. So with that, I'd like to finish for the first hour. I would like to ask if you have any questions.